Okay, welcome to PDEs lecture 16. Today we're going to go on with the heat equation in one dimension and look at how to write down the general solutions using Green's functions. And we're going to show you once again how the different boundary conditions actually lead to different Green's functions. Now, if you can remember in the last lecture, we found that self-similar solution. And then we showed that you could actually, if you were given an initial condition on a boundary, you write down the solution using the self-similar solution. It acted kind of like a Green's function, and we're going to develop that more generally now. Okay, so once again, if I can get going. Okay, so to develop the Green's function for the heat equation, we once again are going to follow a very similar route to what we did with Laplace. Remember, there we basically wrote an equation that was u Laplace g minus g Laplace u. We used Green's identity or the divergence theorem, and then could write down a way of giving the general solution provided we'd had the Green's function. And we're now going to do the same thing. We just have to do it slightly different because the heat equation has both second order and first order derivatives. So we are again going to strive to get something to which we could apply the divergence theorem. It's just slightly more involved. So the way we do it is we say we're going to derive two linear operators. The one is kappa times the second derivative with respect to x prime minus d dt. And the other one is L2. It's a different operator, and it differs from L1 with a sign in front of d dt. Okay, and that often happens if you have first order derivatives coming in, and you'll see why now. Okay, so the reason is we once again are going to try and make this combination so that we can apply the divergence theorem. And instead of now having the Laplace operator over there, we're going to have this operator we've defined. Okay, and notice we're putting the two different operators in. So this guy, L2, is often called the joint operator of L1. Okay, so let's just work out what it is. So firstly, we have V times L1 applied to U. So that is V times L1 applied to U is UXX minus U times L2 applied to V, which is just minus U VXX. Okay, and then we also have V times L1 applied to U, so there's the minus V times du dt, and minus U times L2 applied to V, so the minus over there multiplies the plus, so we also have minus U times V of t. And once again, we want to use a divergence-like thing, so what we now have is, is that expression. Okay, so these last two things, the minus can be written as this complete differential with respect to time, and the second one, the first term over here with the double derivative with respect to x, can be written as this thing in brackets, derivative with respect to x. So the reason why we basically wanted to have different operators is exactly so that we could write this final operator as a complete derivative with respect to t and a derivative with respect to x. So it actually allows us once again to convert a volume integral into an integral on the boundary. Okay. And so if we now go ahead, and I'm going to call that equation 1, and we now want to solve the problem that is very similar to what's basically our heat equation with a source, and the minus sign I've just put in so it's consistent with the previous versions of the heat equation. So we want to solve this problem, And the way we do it is we solve the other problem. Okay, sorry, we want to solve it given initial conditions when t is equals to 0. And on the boundary, we specify either u or ux. Okay, and you'll see from the derivation which one you have to specify. Okay, so it's not a random thing. It's simply I'm just stating it now, but you'll actually see why it's so. And then what we have, and we're going to say we're going to do it like in a box. In other words, there's going to be a minimum x and a maximum x, and we'll know either u or ux on the boundaries, and we'll know our initial condition. So this is the problem we want to solve, and the way we solve it for all f and for all g and all functions on the boundary is we actually solve the different equation for the Green's function and then work out the integral as a result of it. So we're once again going to do let P be a field point and let Q be a source point. Okay, so this is the situation you have. So you have Q being your source point that you typically are going to integrate over some other function and the functions that you're given, in other words, G, F, and the boundary conditions, to try and find out what the solution is at P. Okay, so that's the formal statement of the problem. Let's now see how we do it. Okay, so what we're going to do is firstly our domain that we integrate over goes from t prime goes from 0 to t, and x prime remains in this box. And what we have is, let's now use this identity over here just directly that we've worked out, and we know that L1 of u is the actual operator we want to solve. And so if we do this full integral, we basically integrate over that whole thing, and we multiply with a minus sign. What I've basically got is v times, I've got v times L1 of u, okay, which is minus f, and I've multiplied the whole thing with a minus, so that's f. So it's vf plus the second operator that I actually told you nothing about, but it's there. It simply obeys this property. U times L2 applied to V. And I have that expression, just using this thing that we derived, is equals to XA, XB, because we've written this as a complete differential, and we've multiplied the whole equation through by minus, we have uv, but we now have to evaluate it on the two boundaries. So it is t prime equals to 0 and t prime equals to t. And now the other term that we also have is this term. It's also a complete differential, so we can integrate over x, and we're left with the integral from 0 to t times whatever was in this bracket. So we basically have v ux minus u v of x evaluated on the two boundaries. Okay, so this integral over here, we're basically integrating along from xa to xb, and the second integral over here, we're integrating along that boundary for all time till you get to the time we're interested in, and we're integrating along this boundary as well. Okay, so you can already see that we've done something. When we're talking about u, we basically, the only thing that enters this equation is the function f we know. This one we still have to deal with. This function we know u on the boundary at times t equals to 0. We want to know what u is at times t prime equals to t. And here we know u of x or u on these two boundaries. Okay. So that expression is true. The next step that we're going to go, and we're going to call that number 2, is now suppose we define g which is going to be our Green's function. We define V is equals to G. Once again, it's going to be a function of the field point and the source point. And we say G obeys the operator Laplace is equals to 2G is equals to 0. So everywhere inside omega, but possibly not necessarily on the boundary, this operator is equals to 0, okay, which immediately implies that that term disappears. And the second condition we're going to put on there is if T prime is equals to T, in other words, if we're up here, right, then we're going to say G is a delta function in x prime minus x. And what that gives us, let's just go back. It's cheating. Sorry. My left hand is very unwise. My right hand is not working. So what this thing means is that, look, we have to evaluate G over there at T prime is equals to T, and it's the integral over x. So if we have V equals to G being equals to the delta function at x prime minus x, that basically just means that we have U evaluated at x over there. So there we've got out the actual value of the function we're interested in. Okay, so that then helps us deal with this term. At T prime equals to 0, we know what U is. It's G of x, so we can, that one is fine. And we also know what V is if it obeys these properties, so that one is fine as well. And so the final part is to look at this thing over here, but that one is easy. We know that either V or G must be equals to 0 on the boundary, or it must be equal, its derivative must be equals to 0 on the boundary. Okay, so they're just those two options. And what basically that corresponds to is, remember, we're solving the heat equations. How you can think about it is you're either going to have a boundary where you have lit, like a candle that you're holding it there that's constantly supplying heat, and you know exactly how hot the candle is, in which case you know you're going to be specifying U on the boundary, and therefore you're going to require that G is 0, okay? And if G is 0, then what you're basically going to have is that that term is 0, and you can actually specify U on the boundary and then multiply it with derivative of G with respect to x. The second option is you basically specify that the gradient dg dx is 0. In other words, there's no heat flowing over the boundary, but the actual value can be different. So that corresponds to, you've put it next to a heat bath. So across the boundary, it's like an equilibrium. It just stays there. And you're actually going to see it when we write down the answers in specific examples. Okay, so that's the second case. And you can only have one of these two cases on a particular boundary. What you can have is you can have one case on the one boundary and a different case on the other boundary. In other words, you can specify the function here and its derivative over there, and then in which case you'll look for a Green's function in which these guys are the things that you're specifying, or corresponding ones are actually 0. Okay, so for example, now suppose you were told that that the derivative of U is being specified on the boundary. Okay, then that second condition basically means that that term is 0 and that you just multiply G with the derivative of U to get the answer. Okay, so that thing then gives us a way of actually writing down the answer. And what we have now is just what I've said previously. This term is equals to this term U of G at the different times is basically, I'm just writing out what I've already said, is equals to the delta function at T prime equals to T is just the delta function in x prime minus x. So you get this Ux of T term minus the integral from xa, xb. U, you know, on when T is equals to 0, it's just G prime of x. And G, you also know, when t prime is equals to 0, it's just that. Okay, provided you've now got the G that obeys these two properties. And what you can now do is, if I just rearrange this equation, in other words, so that we have something like u is equal to the rest of the stuff, what I can get is basically something that looks like this. Firstly, so this term is just that term, so we have u of x comma t. I'm going to take this term to this other side, so I'm equals to this integral, okay, plus that term, okay, which is just g times f over integrating over basically your source points. And now finally I must basically move this term to the other side, and I have that evaluated at the two boundaries. Okay, and so I've succeeded in writing down the general solution to the whole problem just using a Green's function that obeys these properties. Okay, so very similar to the Laplace's equation. The only difference is there's a slight difference. Remember, with the Laplace equation, I said basically the operator applied to G is equals to the delta function. You can actually show that this is equivalent to that definition. You can do the same derivation and get that. It's just easier to explain this way because the heat equation sort of goes forward in time. Okay, so but the expressions you get is exactly the same, and you expect them to be exactly the same because you have the uniqueness theorem. So once you've got an answer, you've got the exact answer. Right. So let's now use this equation for a number of examples and see how we get the Green's function, and see how the Green's function actually depends on the geometry and how you specify the boundary conditions, and also get a bit of an intuitive feeling for what the solutions look like. I mean, like Laplace's equation, for example, in the test, what Laplace's equation does, it just takes its maximum on the boundary and then it goes to 0. So in the test you had this thing, like a little hat on the boundary, and all that it basically took that hat and smoothed it down to flat to 0. And you'll see that similar things happen with the heat equation. So I do want to do a number of examples today and just give you a feel for the properties of the solution. Okay, so that's just that very long purple thing that I've now written at the top of the screen because we're going to use it. And the first thing I'm going to do is basically recap, just slightly generalized, it's the case when we're working on an infinite domain. So we already know the Green's function from that, as was hinted to from the last thing, and I'm just going to verify, in fact, that it obeys all the properties we required of the Green's function on the previous slide. So in the infinite domain, we basically let our boundaries go to infinity or plus minus infinity. What we have then is we want to solve this equation, ut minus kappa uxx equals f, given the initial condition, which is equals to g, and with the assumption, and this always happens if you're working on an infinite domain, you always are interested in firstly specifying your data that it's bounded, and secondly specifying the boundary conditions that is also bounded. So this is a little side. If you're working with functions where it's not bounded, it is highly advised to transform infinity to a place where you can actually deal with it more carefully, because otherwise things break apart badly. And that you can do just like 1 over x or whatever, 1 over t will transform your infinity onto a finite domain. So always try and get a function that's got compact support and doesn't explode as you go to infinity, or even remain constant. You tend to have a problem when that happens. Okay, so now let's recall from the last time we expressed the solution in terms of this Gaussian distribution, which is basically what this thing, and I called it delta A, where A is a parameter that goes into this equation that is basically the deviation of the Gaussian. In other words, this thing has an area of 1, but A sets how spiky the hump is as opposed to how flat. Okay, and what we showed in the previous lecture is not only if A goes to 0 does this series of distributions approach the Dirac delta distribution, but if we write set A equals to 2 times the square root of kappa t minus t prime, and we set y equals to x prime minus x, we have a solution that is self-similar, okay, and we can also, in fact, find the Green's function of the solution. So if you remember the last time when I solved the initial value problem, is I basically argued that that g with t prime equals to 0 times the function that you were given would solve the solution. And it's exactly this g that we can just now basically use, and is the same g that appears in these other cases as well. So we basically have this. We're basically going to say, given the experience we had in the last lecture, we're going to use this as an ansatz for our Green's function. And here I'm basically just going to show that this thing actually satisfies all the properties we required of the Green's function. The only statement here is because your because we're working on an infinite domain, and we're basically going to assume that the functions are bounded, and therefore that g of x or the solution doesn't explode at infinity, we're basically going to not worry about these terms, but because at infinity we're basically going to require that the Green's function goes to 0 and its derivative goes to 0. And you can see that typically happens with this self-similar solution, because as x goes to infinity, right, this thing gets very small and approaches 0 actually very rapidly, and the same thing happens at minus infinity. Okay, so the boundary conditions are satisfied. We can basically show that g approaches the delta function as t prime approaches t. Okay, so as t prime approaches t from below, in other words, within the domain, we have a approaching 0, and we know from our series or definition of the delta function that approaches the delta function. So that property is basically satisfied. Okay. The second thing we have is that dg dt is equals to minus gg dt prime. Okay. And you can get that simply from differentiating the actual expression. And you see that you have t minus t prime entering there and t minus t prime entering there, and they're not squared. So this is true, exactly. And so because when we derived the symmetric Green's function, we were actually looking for a solution to this operator in t, we know that this one, if it's dg dt is equals to minus g t prime, we're going to be able to solve the other operator as well. Okay, we also know that gxx is equals to gx prime x prime, and the reason is that it appears quadratically over there, so the minus sign doesn't matter. It cancels each other out after you've taken two derivatives. Okay, so we have that L2 of g is equals to 0, and remember L2 is different from this operator with a minus sign in front of the u of t, so it's exactly right. And we also can just verify directly, as I mentioned earlier, that g and gx approaches 0 as x prime approaches plus minus infinity, so we don't have to worry about these two terms on the boundaries. And what we now have is we can simply write down u of x and t in terms of the initial condition that we're given on the boundary times this integral with our Green's function plus the full Green's function. So this is the Green's function evaluated at t prime equals to 0, and this is plus the full Green's function multiplied by the actual source term. Okay, so this is now our solution on the infinite domain, and all we have to do to write down the answer is, given G and F, we have to now construct these integrals, or do these integrals. And integrals with Gaussians, because they appear in statistics so often, and in fact they appear naturally in nature because you have your central limit theorem. Do you know what that is? Okay, it basically says if you have a probabilistic process followed by a subsequent several probabilistic processes, all the accumulative distributions basically go to the Gaussian. Okay, so it's a very special type of distribution in the sense that most statistical processes eventually limit to this Gaussian distribution. It's a very powerful theorem. Anyway, so statisticians use it a lot, and as a result, people have studied Gaussians very much, and they have very many nice properties, including that cute integral that we did the last time of the area underneath it. But here is also another one. Okay, so if you integrate two Gaussians together with Z, in other words, I've got one Gaussian distribution with Z minus X, and another Gaussian distribution where the argument is Z minus Y, and I work out the integral from minus infinity to infinity, then the result is just a third Gaussian, okay, with a different standard deviation. So the shape of the Gaussian, if I have a spiky Gaussian and this is convolving it with the unspiky ones, I sort of get one in between. And this they use a lot in statistics. And also, there's a lot of other integrals with Gaussians that you can actually look up either in Mathematica or Oscar when you integrate it, or there are tables. And I can give you a link to sort of tables with lots of integrals in, which is if ever you get a problem, you can go there and you can actually look up what your integrals are. But Gaussians are very well known. And anyway, this particular integral makes it easy for us to just look at several examples. So what I'm going to do now is just actually write down the answer. And what I'm going to choose is, suppose I start, and I'm going to look just at this term to start. So what I basically have is an infinitely long rod. I give it an initial heat profile. And I'm going to do two cases. I'm going to do one where I have this blue fat Gaussian over here, and then I'm just going to basically work out what this term is. Okay? And you can see what the answer looks like. So our initial condition is simply a Gaussian there, and the answer you can actually work out exactly when you integrate the two together. And what you get is basically you have the hot spot or the peak of the Gaussian over there, and what I've drawn here is contours of equal U value. Okay, so you can imagine initially on the boundary you have this high spike, and then as time goes on the heat diffuses away exactly as you anticipate it to behave, and then what I've basically drawn is just these equipotential contours, and you can see it just like goes further and further away. So once again, at the end of last lecture, we worked out that maximum value theorem, or the maximum value of the source-free case. This you actually see it. It's a spike that's on the boundary. Very, very similar to Laplace's equation. Okay, but it's different. The rate at which it flows away goes like t minus t prime, and that's not the same case with Laplace's equation. Okay, but it actually looks the same, just superficially. Okay, so now let's have a look at this one where we start an initial condition, also g of x, and we once again just work out this integral. So we now have two Gaussians separated by a certain sort of centered at 1.5. Or no, centered at 1. And then these integrals you can actually do analytically as well. And let's just look at what the answer looks like. Right, so you basically have your two Gaussians over here, and your two initial spikes are like that. And I think, if I remember correctly, I actually chose the heights of these Gaussians that the total heat, I normalized them so that the total heat was the same. And what you can see is initially you have these two hotspots, and after a certain amount of time, it actually looks exactly the same as this other heat thing. It eventually approaches the spreading total Gaussian. And you'll actually also be able to prove that analytically if you wanted to. You take the limit as time goes large, and you can actually see that the shape becomes very, very similar to the same thing. So there's a very intuitive feeling to what these solutions will actually look like, and it's borne out in the mathematics that you can solve exactly. Okay, so that's an infinite domain. What happens if we put a boundary over here, right? And that's what I'll do next, and you'll see the actual solutions changes as a result of the boundary condition. So it's important to know that your Green's function, just like in Laplace's equation, is a product of your Green's function that sort of has the delta function spike over at x prime minus x, and a component that makes sure you satisfy the boundary condition. And so if we have the finite domain, or semi-finite domain, the first thing we're going to do is we're going to bring in a distinct boundary at, say, at x equals a, we're going to say, we're going to move xa from infinity to 0, and we're still going to have b go to infinity. And then the problem statement's basically the same, the heat equation, initial condition g, f and g bounded, and we are going to now use this full expression, which I've just put at the top over there, and we want to construct a Green's function that obeys the properties we have previously. And once again, just like we did in Laplace equation, where we sort of used a symmetric solution and then combined it in clever ways, we're going to do that with the heat equation as well. And so here is our symmetric or our self-similar solution on the infinite domain. We know that the Laplace of this thing is equals to 0 inside the domain. We also know that on the boundary as t equals to t prime, this thing approaches the delta function. Okay, so we've got our delta function. The thing that we are lacking is, the other thing I'm just going to work out quickly is, let's take the derivative of g with respect to x prime. Okay, so it's basically the derivative of this thing with respect to x prime. So we basically have the exponent remains the same, minus 2 times x prime minus x over 4 kappa t minus t prime. Okay, so the 2 cancels. And then we'll times whatever remains, which is g of s. So that's just a derivative with respect to x prime. And if we have, the first case we're going to consider is we want boundary conditions where u of 0 and t, so over here, is given. Okay, and we're going to give the actual value of the function rather than the derivative. And you'll see, and I'll do the one where we give the derivative in a moment. Okay, so we basically seek g such that g at x prime is equals to 0. So clearly, this thing is not enough, okay, because at x prime, when x prime is equals to 0, it has a definite value that depends on all sorts of things. But the cool trick is, okay, and we want these conditions at infinity, and this guy automatically solves that. So we don't have to worry about those. We have to try and get this thing to work. And the way we get that thing to work is we subtract another function that has the same value at x prime is equals to 0, but it doesn't change these two properties. Okay, so if we were to do this thing, we can see firstly that if we make the difference between these two and we evaluate it at x prime equals to 0, then because this thing is quadratic in x, It's actually 0, this difference. Okay, do you see that? Okay, so that's good. The only thing that we must be careful with is if we have this g of s with minus x, we know that as t goes to t prime, it's going to approach a delta function at x prime minus x, so at x prime plus x. But, so the delta function only gets a spike in the region when x is negative, or right? So that delta function doesn't impact it. So once again, it's the same as what we did with that method of images. We had a function that had behaved all the properties, and the place where it had a spike was outside the domain, so it was fine to add it back, and this is exactly what we've done. So over here, this combination actually gives us all the properties up here that we need from this one. This guy also has that property, okay, but it doesn't get the delta function, so that's fine. And it has the property that the boundary condition is equals to 0 when x prime is equals to 0. So very important, when you work with the Green's function, you always are working in x prime. But when you write down the solution, it's in x, hence the difference between your source and your source and your field point. Okay, so if we do that, so that's enough to prove that this g is actually the correct Green's function for the Dirichlet boundary conditions, and here we can write down the solution. So here we once again have that at g, the initial condition is just g of x prime, the product of the two Gaussians, the sort of the standard deviation of the Gaussians are the same. And and the source term is once again the full Green's function now, times the forcing term. And what we further have is our boundary condition here at x is equals to 0 is equals to the integral of 0 to t times basically we have that one. So it's the derivative of g of x minus in front and multiplied by u. So there's this. Okay, so this is just the derivative of minus the derivative of g of x evaluated at x prime is equals to 0. Okay, so there we have it. So that's the full solution on our semi-infinite domain. And once again, you can work out the integrals to get an exact answer, and let's do it now, because it's kind of interesting to see how things happen. So what I'm first going to do is give exactly the same initial condition that we had in the previous case, okay, and give no boundary condition. So I'm actually going to set the boundary condition equals to 0. And you're going to see, even though the boundary condition is equals to 0 and the initial condition is equals to the same, the answer is different in the infinite and the semi-infinite domain. In fact, not much different, it is just different. So here you can see, here's our initial condition. It still looks like a spreading Gaussian, but it's not as symmetrical, because you can see the boundary condition over here where we've set u to be strictly 0 basically fixes it, and the heat flows smoothly, very similar to what it did in the past, but it doesn't go across the boundary. It's simply the boundary condition that's been forced. So here you again can have this initial heat spike over here, and then the heat flows in, 0 on the boundary. And so what I'm going to do now, just to show you what the boundary condition is like, is suppose I have a boundary condition like this in time. Also just a Gaussian once again, because it's easy for me to do the integrals and illustrate things. And in fact, you can actually decompose almost any function to Gaussians if you want. So it's a good way of thinking about it. And so what it looks like if you do the second one, so this is the case where I start with a rod that is 0, okay, initially, and then the end I basically, for like a Gaussian, I sort of bring a flame slowly closer, and then I heat the rod a bit, and then I take the flame away, and you can see how the heat changes in time over here. Okay, so there's a very natural feeling to what your solution should be like. And this is the exact analytic answer to this term over here. Well, I actually just computed the integral. And you can see because the equation is linear, you basically, if you wanted both these two together, you would simply add the two terms. And you would have this spike with this thing added together linearly, and that would be the valid answer. Okay, so similarly, if you were to have the initial condition 0, the boundary 0, and then you would bring a flame up to the rod for a bit and then take it away, then you would be evaluating this term. And you would also see the heat flow in time, just as what you go on. And once again, also, the total heat is accumulative, right? So the more heat you put in, the more heat you've actually put into the system. Okay. So that's the semi-infinite domain for Dirichlet boundary conditions. Okay, and that's basically specifying the function. Let's now see what happens when you have Neumann boundary conditions also on the semi-infinite domain. And once again, what's going to happen is we're going to construct our Green's function out of our self-similar solution. So the semi-infinite domain, once again, exactly the same boundary conditions, same heat equation, specified initial condition, the condition on the functions, except that now we can actually specify the derivative of u of x on the boundary. So we are looking for a Green's function where the derivative of the Green's function is equals to 0 at x. Once again, we start with the properties of our symmetric Green's function. We have the self-similar solution. It obeys the operator equals to 0. This Green's function approaches the delta function on x just by definition of what the series of Gaussians actually does. And there we have the derivative, that I computed the last time of the Green's function itself. And I've just evaluated it, x prime is equals to 0. So now the Neumann boundary conditions is we basically seek the derivative of the Green's function equals to 0. Okay. Oh, so this is the one thing that's specified. We've got the derivative of u specified on the boundary, and therefore we want the derivative of the Green's function to be 0 as well. And the Green's function must be bounded as x goes to infinity, which will be guaranteed if we're building it up out of the symmetric Green's functions. And so let's have a look at this thing. Okay. So if you make the sum of the two, once again, you're adding a second Green's function that has its delta function spike that's outside of the domain. So you don't change this property because the delta function appears for negative x. And it inherits all these other properties, so you can actually prove that this full thing satisfies everything you need. Okay. And you can also prove that its derivative, okay, at x prime is equals to 0 is just this. Okay, so here we have g, and careful, the first naive thing would be to say that this derivative at x is equals to 0 is 0 because of that, but that's not what you're looking for. You're looking for the derivative in x prime equals to 0. Okay, so don't be too quick over there. So I simply write down what this thing is from this definition over here, and we have that it's xg of xt 0 t prime, t minus t prime, and it's this thing, x times gs of minus xt 0 t prime over that thing. But the key point is that because you're quadratic in x, then these two are the same. Okay? And that's why it cancels, not because this x is equals to 0, because this thing holds true, or this expression must hold true for all of x, all of t, and all of t prime. Okay, but it is 0 because it's quadratic in x, and so we've actually got a Green's function that obeys all the properties, reasonably easy to construct, because it's just the sum of the one. Remember the Dirichlet boundary conditions, you had a minus over there. Okay, and we can now write down the full solution. If we have Neumann boundary conditions, it's simply the initial condition contribution, where we now have a plus, the forcing term contribution with the Green's function in here, and this is evaluated at t prime equals to 0. There's a t prime in there, it's the general Green's function, and the boundary term, where we basically have the derivative of u of x multiplied by the Green's function itself over there. Okay, recall when we were doing Dirichlet boundaries, we had the derivative of the Green's function coming in. And once again, we can now look at an example, and I'm going to do exactly the same example, or the same initial conditions, just to show you how it differs. So it's just, now what I'm going to do is it's basically this first term where I've conducted the integrals. So once again, if I have G being a Gaussian, which is basically the blue Gaussian over there, I can work out the integrals with another Gaussian and the integral with this Gaussian exactly. And the solution is now looks like this. Okay. And it's very different from the one where u is equals to 0, but it's the right answer because, look, I haven't specified the boundary condition. I've basically implicitly meant, if I look at just this term, that the derivative of u on the boundary must be 0. And if the derivative of u of x on the boundary is 0, all the lines come in horizontally. Okay, so I have got the correct solution. So always do a sort of a reality check when you work out these terms, right? Write down or trying to find a way of plotting the solution you found, and make sure that at least if you've specified 0, the Neumann boundary conditions in these things have to basically be orthogonal coming in here. Okay, and that basically means that the heat profile doesn't change across the boundary. Okay, so it's sort of an equilibrium. And now if you actually add the boundary condition in here, remember what we're doing is we're specifying the derivative of u, of x, on the boundary. So we basically are specifying the slope of the contour lines coming in. And you get something like that. Okay, so here you have basically your heat term, and just the scales of these two things are not the same, actually. I had a dynamic scaling that I couldn't fix. Here you have your initial condition, and then here you have the term, and that you see here as you get closer to the peak of the boundary, the slope of your incoming, of your contours becomes more and more vertical as the initial, or as the boundary condition changes. And then here, far away, when the Gaussian has disappeared or goes to 0, you're again orthogonal to your boundary condition. Okay. So it just gives you an intuitive feel of what these solutions actually behave like. Okay, the next one, but I think I'm actually going to do it tomorrow because I want you to go through these things. The next thing I'm going to do is actually look on a finite domain. In other words, if you have x equals to 0 and say xb equals to a, I'm also going to try and work out the Green's function. But this time I'm going to, just as what we did with Laplace's equation in the box, where we made that, basically did a Fourier series expansion, I'm going to do that, use that technique, which is a slightly different method of finding the Green's function rather than constructing it out of the Self-Summer solutions. Okay, so then you can actually sort of be fresher from when you do that. But it would actually be useful if you print out this lecture and just bring the pictures along so that you can compare it with what I show the next time. And then you can actually see how it changes there as well. Because the same properties of the Neumann boundary condition solution being different to the being different from the Dirichlet boundary condition, being different from if you look on infinite domain, also holds true, except that you have this type of thing now happening on this boundary as well. Okay, so you can sort of almost guess what the answers are going to look like, but finding the Green's function is a little bit technically tricky as well. But it does give us a difference technique. Any questions at this point? Okay, cool. So let me stop the recording.